Welcome to the deep dive. Today we're tackling, well, just a monster of a tech story, NVIDIA. How did a company that, started out making graphics cards for PC games become the absolute engine of the AI revolution? We're talking about a company that briefly topped Microsoft and Apple, hitting, what was it, $3.34 trillion in market cap back in June 2024. Just wild.
It really is hard to wrap your head around that number. I mean, that's more value than the entire GDP of countries like Australia or Russia or South Korea. It's just huge.
Right. And it obviously didn't happen by accident or overnight.
No, definitely not. And crucially, it wasn't just about having faster chips. That's part of it, sure, but not the whole picture.
Okay, so that's the puzzle for you, our listener. How did they actually build this incredible dominance? Our sources point to this mix of, seeing things early, sticking with software investment for decades, and this whole strategy of vertical integration.
Yeah, the full stack approach.
Yeah.
They didn't just want to sell you a graphics card. They wanted to sell you the whole computing system, all working together perfectly.
So our mission today is to take this really complex story, silicon, software, networking, all of it, and break it down. We're going to try and use that Feynman technique approach.
Right. Explain things simply, cut through the jargon, figure out how the system works, and maybe most importantly, point out what we still need to figure out. What are the gaps in understanding for you to explore next?
Exactly. Let's start this deep dive then, back at the beginning, which funnily enough was at a Denny's.
Yeah, the legend is true. 1993. Jensen Huang, Chris Malachowski, Curtis Prime, they supposedly mapped out the company's future on napkins at a Denny's in East San Jose. There's even a plaque there now, apparently.
Oh, amazing. But these weren't just, gamer guys, right? They came from serious tech background.
Oh, absolutely. They were engineers from places like Sun Microsystems, LSI Logic, high-performance computing, workstation stuff. Their big idea wasn't really about games per se.
It was about the tech behind the games.
Exactly. They saw this super expensive 3D graphics tech used in professional workstations, and their goal was basically to bring that power down to the, affordable PC market, democratize it.
And the name NVIDIA, I heard it came from next version.
That's the story. Their working files were labeled NV for next version. So they looked around, found the Latin word NVIDIA, meaning envy.
Hence the green eye logo and slogans like green with envy. Okay, makes sense. They were definitely signaling ambition.
For sure. But, that ambition wasn't exactly met with open arms at first. When Jensen Huang went pitching to venture capitalists on Sand Hill Road.
They weren't buying it.
Not really. The famous quote is something like, people don't start companies just so people can play games.
Yeah.
Shows you how much of a long shot it seemed back then. They were betting on a whole market shift.
But they kept at it. And that led to the big breakthrough, the GPU itself, 1999, the GeForce 256.
Right. The first chip they actually marketed as a graphics processing unit, a GPU. And this is probably a good spot to pause and, really simplify that core idea. What is a GPU versus a CPU?
Okay, yeah, good idea. CPU first, central processing unit. That's the brain of the computer we all knew.
Right. And it's designed for sequential work. Think of it like having maybe, 4 or 8 really smart, really capable managers. They can handle complex tasks, logical stuff, but they do things mostly one after another. Step-by-step problem solvers.
Got it. So complex sequential tasks. And the GPU.
The GPU is built completely differently. It's all about parallel processing. Instead of a few super smart cores, it might have thousands of simpler, smaller cores.
Thousands, wow.
Yeah, and its strength is taking one massive but kind of repetitive task, like rendering all the pixels in a 3D scene, or doing the same math operation millions of times for AI, breaking it into tiny pieces and having all those thousands of cores work on those pieces at the same time.
So it trades that deep, complex logic for just sheer parallelism, brute force concurrency.
Exactly. That's the fundamental difference.
Right.
And that parallel design is key to everything now. But they didn't get it right immediately. Their very first chip, the NV1 back in 95, total flop.
Ouch. What went wrong?
Well, a couple of things. It was too expensive, for one, but the bigger issue was technical. NVIDIA had bet on a rendering method using something called quadratic primitives.
Okay.
But the whole industry, led by Microsoft with its DirectX software, was standardizing on a different method, triangle primitives.
So the NV1 basically didn't work with the new standard software everyone was starting to use.
Pretty much, yeah. One partner famously sent back almost all the units they bought. It was a near-death experience for NVIDIA. They were apparently only saved by a payout from a canceled contract with Sega.
Wow. Close call.
So close that it led to this unofficial internal motto they still apparently use. We're only 30 days away from going out of business. A constant reminder.
That must focus the mind. So what did they learn?
They learned not to fight the market standard. They stopped trying to push their own way and just fully embraced Microsoft's DirectX. And the next chip, the Riva 128 in 1997, was a huge success because it worked seamlessly with the ecosystem. Lesson learned.
Okay, so they figured out the hardware for gaming, massive parallel processing. But how do you get from making games look good to powering like global AI research? When did they realize that gaming chip was actually perfect for something else entirely?
Well, the realization was kind of elegant, really. It turned out that the type of math needed for complex 3D graphics, tons and tons of parallel matrix calculations, was almost exactly the same type of math needed for training these deep learning AI models.
Ah, so the hardware was already the right shape for the job, they just didn't know it yet.
Sort of, yeah. But the hardware was locked. You couldn't just use it for anything other than graphics. It needed software to unlock that potential.
And that software was CDA.
CUDA, Compute Unified Device Architecture, released way back in 2006.
Hmm.
And we really need to slow down here because it's arguably the foundation of their current dominance.
Okay, so it's not just like a driver update.
Oh, not at all. Think of it as a whole software platform. An API, compilers, libraries, tools, everything a developer needed to write code that could run calculations directly on those thousands of GPU cores for things other than graphics.
So it turned the graphics card into a kind of programmable supercomputer add-on.
Basically, yes. It unlocked all that parallel power for general-purpose computing, and scientists and researchers jumped on it. We see in the sources people at Stanford, later Jeffrey Hinton's group in Toronto, they found they could run their deep learning experiments using CDA.
And it was way faster.
Like 10 times faster. Sometimes even 100 times faster than using just the regular CPU. Imagine the difference that makes to your research cycle time.
Huge. And this is where that software mode idea comes in, right?
Exactly. Because NVIDIA got there first with a stable, well-supported platform, the entire research community, academia, early AI startups, they built all their important tools and frameworks like TensorFlow, PyTorch on top of CDA.
So everyone learned CEA, all the foundational code was written for CDA.
Which created this massive compounding advantage. It became incredibly difficult and costly for anyone using NVIDIA GPUs to switch to a competitor, even if the competitor's hardware looked okay on paper. The switching cost was astronomical.
But wait a second. Competitors aren't just sitting still, right? AMD has their own thing, RSCM. Google built TPUs specifically for AI. Why isn't that competition eroding the CUDA moat more?
That's a really important question. And the sources suggest the answer isn't just about the raw chip speed anymore. Yes, NVIDIA chips are fast, but a huge part of the performance advantage today comes from that whole co-designed software stack.
Meaning it's not just CUDA itself, but all the bits around it.
Precisely. It's the whole ecosystem. It's the highly optimized math libraries you hear names like Qbless, QDNN. It's the way it integrates with compilers and debugging tools. If you're a big AI lab and you try to switch your massive code base to run on, say, AMD's ROCM,
things might break. Or just run slower.
Often, yeah. Or you suddenly need specialized engineers just to figure out low-level stuff that NVIDIA already smoothed over years ago. The friction, the developer pain, that's the real moat now. It's 2 decades of development leap.
Okay, this feels like a good spot for our first analogy to kind of lock this in.
Let's try one. Analogy 1. The custom tooling and ecosystem. Think of the GPU as this incredibly powerful, specialized engine. Now, CUDA isn't just the engine's operating system, it's the entire custom toolkit that comes with it. The perfectly paved roads designed just for that engine, the specialized fuel, the expert mechanics on call, the application store full of optimized apps.
Okay.
Now, competitors might sell you a pretty fast engine too, but they basically hand it to you and say, good luck, build your own roads, figure out the fuel, find your own tools, even if their engine is, say, 90% as powerful in theory.
In the real world, using their less mature tools and roads, you might only get 50% of the performance.
Exactly. The whole system matters, not just the engine specs. The ease of use, the pre-built libraries, the reliability, that's the CUDA advantage.
Which makes NVIDIA's decision back then to really pivot the whole company towards this accelerated computing thing seem pretty bold.
It was huge. They weren't just dipping a toe in AI. They apparently made a wholesale pivot in R&D, shifting resources away from just chasing incremental gains in graphics or fighting the CPU guys.
They saw they could get these X factors of improvement, like huge multiples of speed up, in AI.
Yeah, they bet that focusing on this new type of computation, enabled by their parallel GPUs and CGO, was a much bigger opportunity than trying to get, another 15% performance boost in the crowded CPU market. It was a massive bet on a future that wasn't obvious to everyone back in the mid-2000s.
But it positioned them perfectly when the AI explosion finally happened a decade later.
Absolutely. They weren't just selling hardware anymore. They were selling the key to unlocking a whole new kind of computing.
Okay, so CGPA created this incredible software advantage, this moat. The next logical step seems to be control the whole environment to maximize that advantage.
Right. If the software is your edge, you want to make sure the hardware and the connections run it as efficiently as possible. So NVIDIA shifted strategy again. They moved from just selling chips.
To selling entire integrated systems, the DGX servers, those HGX blueprints, the massive SuperPOD clusters.
Exactly. And this shift from being a component supplier to a systems vendor is maybe the most critical strategic move after CDA itself.
Why was that so important?
Because AI models just kept getting bigger. We went from billions of parameters to trillions. Suddenly, these monster models couldn't fit onto just one server, no matter how many GPUs you crammed in.
So the work had to be spread out,
Yeah.
distributed across lots of machines.
Precisely. You might have hundreds, even thousands of GPU servers all working on the same training job.
And that creates a new problem, right? How do you get all those machines to work together efficiently?
That's the bottleneck. You need them to act like one giant unified computer, one coherent compute engine, as they say. And for that, the connections between the servers become absolutely critical. You need super high bandwidth and incredibly low latency.
Otherwise, the GPUs are just sitting there waiting for data.
Exactly. The network becomes the weak link. And Jensen Huang saw this coming. He famously said something like, networking, more than compute, is the future of the data center. The compute itself has to sort of extend out into the network fabric.
Which brings us to Mellanox.
Mellanox.
Yeah.
The huge acquisition in 2019. NVIDIA spent, $6.9 billion, almost all the cash they had on hand at the time.
That's an incredible amount to spend on a networking company. Why buy them outright? Couldn't they just partner or use Mellanox chips?
Well, think about that systems approach. If the network is the critical bottleneck, and you want guaranteed predictable performance for your whole DGX system, you can't leave that crucial connection piece to someone else. You need to control it.
You need to tune it specifically for your GPUs and software.
Exactly. Mellanox was the leader, the undisputed leader, in high-performance networking for supercomputers and data centers. Buying them meant NVIDIA could unite their GPU acceleration with Mellanox's top-tier networking and storage tech. The goal was explicitly to build data center-scale computing architectures. They had to own the whole data path.
And what specific technologies did Mellanox bring that enabled this? You mentioned network adapters and switches.
Right. Two key things. First, they're ConnectX network adapters. These are the cards that plug into the servers, the NICs. And Mellanox NICs often had special hardware built in to speed up network tasks, taking load off the CPU.
Okay. And the switches?
The Spectrum switches. These are the boxes that actually form the backbone of the network, directing all the traffic between the thousands of servers in a big cluster. By owning both the adapter cards and the switches, NVIDIA could design and optimize the entire path.
So when a customer buys, say, a DGX SuperPOD,
they're not just buying a bunch of powerful servers. They're buying a pre-validated, optimized system where the GPUs, the CUDA software, the ConnectX cards, and the Spectrum switches are all designed and guaranteed to work together seamlessly.
which cuts down on headaches for the customer and gets their AI models trained faster.
That's the value proposition. Less friction, faster time to results. That's huge when you're spending millions on training runs.
Okay, let's try our second analogy here to really nail this networking piece.
All right. Analogy 2. Owning the transportation infrastructure. Think of the GPUs as those super fast race cars again. And the data they need is the fuel. Before Mellanox, NVIDIA had the fastest cars, but they were driving on, regular public roads, sometimes congested, sometimes slow, run by different companies or cities.
Okay, makes sense.
After buying Mellanox, NVIDIA now owns and operates its own private, super high-speed highway system. Think dedicated lanes, optimized on-ramps, perfectly synchronized traffic lights, all built specifically for their race cars, the GPUs, carrying that high-value fuel, AI data. They control the whole infrastructure, from the engine to the road, ensuring the fastest possible journey.
That clarifies it nicely. And wasn't Intel also trying to buy Mellanox?
Yeah, the sources mentioned Intel was definitely interested. Reportedly bid somewhere in the $5.5 to $6 billion range. NVIDIA paid a premium to get it done.
Why would Intel want them? Just to keep them away from NVIDIA?
That was likely part of it, but Intel probably would have faced more regulatory scrutiny, especially around controlling the InfiniBand standard, which is used broadly in high-performance computing, not just with NVIDIA gear. NVIDIA swooping in and integrating quickly was key.
And this whole vertical integration thing, controlling the stack, also explains why Jensen Huang keeps saying they aren't going to build their own general-purpose ARM CPU, right?
Exactly. His logic, according to the sources, is all about focus. Where can NVIDIA get those massive X-factor improvements? He believes it's in the GPU, the networking, and the software that ties it all together.
Not in the CPU market where gains are maybe 10–15% a year.
Right. Why fight that battle when you can dominate the acceleration and interconnect space? He'd rather partner with CPU makers, Intel, AMD, ARM vendors, and pour NVIDIA's R&D into their core strengths.
Which brings us to the practical side, the costs. Because running these systems isn't cheap.
No, definitely not. And this leads us to our first big knowledge gap for you, the listener, to think about.
Okay, let's hear it.
Knowledge gap 1, networking TCO. Okay, operators building these huge AI factories often use a mix of gear. They're constantly weighing the options. So what are the real cost of ownership, the TCO trade-offs? Specifically, comparing using that top-tier super-fast InfiniBand network from Mellanox versus scaling up a really modern AI-optimized Ethernet network.
So it's not just the upfront cost of the hardware.
Right. You need to factor in everything.
Mm-hmm.
Specialized staff may be needed for InfiniBand, power consumption differences, licensing, how often things fail, how long the hardware lasts.
Mm-hmm.
All of that feeds into the true cost over time. Understanding the calculation is key to see where the market might shift.
Okay, let's dig into those two networking technologies Mellanox brought, InfiniBand and Ethernet. You mentioned them, but maybe we can simplify the difference for listeners.
Sure. So InfiniBand is kind of the thoroughbred racehorse of networking. It comes from the world of high-performance computing, supercomputers. Its whole design philosophy is about achieving the absolute lowest latency, the delay in sending data, and the highest, most predictable bandwidth.
So for the biggest, most demanding AI training clusters, InfiniBand was the gold standard.
Historically, yes. It was a big reason Mellanox dominated that high-end market. It drove like half their revenue.
Okay, and then there's Ethernet.
Ethernet is, well, it's everywhere. It's the standard network technology in almost every office, every home, every data center. It's generally cheaper, much easier to integrate if you have equipment from lots of different vendors, what they call mixed fleets.
But maybe traditionally not quite as fast or low latency as InfiniBand.
Traditionally, yes. But Ethernet technology has been improving really fast, especially with things like smart NICs, network cards, they can do some processing themselves, and new intelligent switch fabrics. So high-speed Ethernet is definitely catching up for AI workloads.
So operators face this choice. Do they go with the ultimate performance of InfiniBand, which might be more complex, or lock them in more? Or do they use this improving flexible Ethernet that might be cheaper initially?
That's the constant balancing act. And NVIDIA, owning Mellanox, is trying to push the boundaries on both fronts, making their Ethernet offerings faster and more feature-rich for AI.
Now, you mentioned something really interesting earlier, extending NVLink across the network. Can we unpack that? What is NVLink normally, and how would it work across servers?
Okay, yeah, this is pretty cool. Potentially game-changing. So NVLink today is NVIDIA's super-fast proprietary connection inside a server. It's how the multiple GPUs within a single DGX box talk directly to each other, bypassing the standard, slower PCIe bus. It gives them massive bandwidth and low latency for sharing data locally.
Okay, so it connects GPUs inside the box.
Right. The big idea, enabled by Mellanox's tech, is to effectively stretch that NVLink connection outside the box, across the network fabric, to connect GPUs in different servers, almost as if they were in the same machine.
Wow, how would they even do that?
It relies on some key underlying technologies Mellanox was expert in. One is RDMA, which stands for Remote Direct Memory Access.
Okay, what does that do?
Basically, RDMA lets one computer's network card write data directly into the memory of another computer without having to bother the CPU on either machine. It cuts out huge amounts of overhead and latency.
So direct machine-to-machine memory access over the network.
Exactly. And building on RDMA, there's another protocol called NVM of F, which is NVM Express over fabrics. NVM Express is the fast way modern flash storage talks to a computer. NVMe of F uses RDMA to let servers access flash storage located in other servers across the network almost as fast as if they were plugged in locally.
Okay, I think I see it. By combining RDMA and NVMe over those fast Mellanox fabrics, you can make a whole rack of servers act like one giant computer with shared memory and storage.
That's the goal. The network fabric essentially becomes an extension of the computer's internal bus. It's how you achieve that coherent compute engine across hundreds or thousands of nodes. Truly systems-level thinking.
It's incredibly sophisticated engineering, but even with all that control, they still bump up against hard physical limits, right? Especially now with this massive surge in demand for generative AI.
Oh, absolutely. The demand shock basically turned AI training from a niche academic thing into like national scale infrastructure overnight. And that immediately exposed some serious bottlenecks in the physical supply chain.
Right.
Stuff that just throwing money at doesn't fix quickly.
Things like actually packaging the chips. You mentioned CoWoS.
Yeah, CoWoS chip on wafer on substrate.
Oh.
It's a fancy way of saying it's a very advanced technique, mostly done by TSMC, for packaging the huge AI GPUs together with their specialized memory.
What's so hard about it?
It involves placing the main GPU chip and several stacks of memory chips very precisely onto a middle layer called an interposer. This interposer has incredibly tiny connections. It's complex, uses unique expensive tools, and the manufacturing yield, the percentage of good chips you get, is lower than standard processes.
So even if TSMC can make the raw silicon wafers fast enough, the step of actually assembling the final package with the memory is slow and capacity limited.
Exactly. It became a major bottleneck globally. And that ties into the other key component limitation, HBM, high bandwidth memory.
Right, the memory that sits right next to the GPU on that package.
Yeah. HBM involves stacking memory chips vertically, which gives you incredible bandwidth data transfer speed essential for feeding those hungry AI models. But producing reliable, high-yield HBM is also really difficult and expensive. So HBM availability is another constraint on how many top-end GPUs can be built.
Okay, so packaging and specialized memory are bottlenecks. What about just power? I saw a source mentioning future AI power needs could rival entire countries, like Netherlands.
That's the often overlooked third leg of the stool. We focus on the chips, but these dense clusters of high-powered GPUs, like in a DGX SuperPOD, draw enormous amounts of electricity and generate immense heat.
So the data center itself becomes the limit.
Increasingly, yes.
Yeah.
Can the facility actually get enough power? Can it dissipate the heat, often needing complex liquid cooling systems now? Is there enough physical space? You can have the chips ready, but if you can't physically install and power them efficiently, you're stuck. Power density, cooling, and real estate are becoming hard limits to growth.
So you've got these physical limits, packaging, memory, power, colliding with geopolitics, which forces NVIDIA to make different chip versions for different regions and pushes countries to build their own AI infrastructure.
Exactly. It's a complex interplay. And that brings us neatly to our second knowledge gap, something critical for you to dig into.
Let's have it.
Knowledge gap 2?
Yeah.
Supply chain constraints.
Okay.
Considering these intense bottlenecks as specialized CoWoS packaging, the HBM supply, and the massive power and cooling demands, which constraint is likely to be the ultimate long-term ceiling on AI growth. Will it be the ability to manufacture and assemble enough advanced chips? Or will it be the ability to physically deploy them the limits of power grids, cooling technology, and data center real estate? Where will the breaking point actually be? Because where you think that limit lies drastically changes investment strategy.
Right. It really underscores how NVIDIA's dominance makes sense because they tackled that whole system. And now their tech is just everywhere, often behind the scenes.
Totally. You look at something like Amazon Web Services, AWS, which basically runs a huge chunk of the internet, maybe 30% of the cloud. NVIDIA tech is deeply embedded in their compute, their data analytics infrastructure.
And for anyone wanting to train a really big state-of-the-art AI model,
NVIDIA GPUs are pretty much the standard choice, whether it's the giant labs building foundational models or companies like Tesla using, reportedly $50,000 NVIDIA GPUs for their full self-driving training clusters.
the OpenAI connection is fascinating too. NVIDIA backed them really early on, didn't they?
Yeah, great example of foresight. Jensen Huang himself apparently hand-delivered the world's first DGX supercomputer to OpenAI way back. That cemented a relationship that's obviously huge today, with OpenAI talking about future systems linking maybe up to 1 million NVIDIA GPUs.
1 million. The scale is just mind-boggling, and the financial impact followed, obviously, hitting that trillion-dollar valuation in 2023.
And you could even see geopolitics in their revenue numbers. The sources note that in 2023, a bigger chunk of their revenue started coming from the U.S. market.
Which lines up with the explosion of US-based AI companies and the fact that the US is spending way more than, say, China on building out domestic AI infrastructure right now.
Exactly. And then they did that 10-for-1 stock split.
Which made the shares cheaper individually, right? More accessible.
Yeah, basically lowering the price per share made it easier for more retail investors and even some institutions to buy in right when global interest in AI infrastructure was peaking. Good timing.
But NVIDIA isn't just sitting back and enjoying the data center boom, are they? They're looking ahead.
Definitely not. They're placing some big bets on what they see as the next major wave, physical AI.
Physical AI, meaning AI that interacts with the real world.
Exactly. Think robotics, autonomous vehicles, drones, AI running directly on devices at the edge, not just in the cloud, making decisions and taking actions in physical space.
And how are they positioning themselves for that?
Well, partly through internal R&D on platforms like their Jetson Edge AI modules and Isaac robotics simulators, but also through strategic investments, like putting $50 million into Figure AI.
That's the humanoid robot startup.
That's the one. And they invested alongside people like Jeff Bezos and OpenAI. It's a clear signal that NVIDIA plans to be the computing engine inside those future robots, powering the embodied AI of tomorrow.
So this brings us back to a really practical point for anyone listening who's involved in buying or planning AI infrastructure.
Yes. The crucial takeaway, if you're looking at this from an operator's perspective, is you absolutely cannot think about AI spending as just buying the chip with the highest theoretical speed rating.
You have to think like a systems engineer.
Precisely. It's a balancing act across that entire stack we've been talking about. The GPUs, yes, but also the specialized HBM memory, the right network fabric InfiniBand or Ethernet from Mellanox, the power delivery, the cooling system, and critically, that mature CUDA software ecosystem.
Because the real goal isn't just hitting the highest number of FLOPS floating point operations per second on paper.
No, that's almost a vanity metric these days. The real metrics that matter, the ones that drive the business case for buying NVIDIA's integrated systems, are things like the lowest cost per token generated by your language model, or the fastest time to first useful model. How quickly can you get value? That's what dictates profitability and competitive advantage. Hashtag tag outro.
Okay, so if we try to boil down NVIDIA's incredible run so far, what are the absolute key takeaways?
I think it comes down to a compound advantage, really built on maybe three main pillars. First, that huge 2-decade head start on the software and developer tools with CUDA. That moat is just incredibly deep.
Right, the software lock-in.
Second, the foresight and willingness to make that massive company-wide pivot towards AI and accelerated computing long before it was obvious.
Big bet.
And third, the strategic commitment to vertical integration controlling the whole system, especially that critical Mellanox acquisition, which let them own the network bottleneck just as AI models exploded in size and demanded that data center scale coherence.
They went from hardware to software to full systems, from a diner napkin to dominating global compute infrastructure.
This is an amazing story. But, the game isn't over. The landscape is constantly shifting, especially with policy and regulation playing such a huge role now.
Yeah, things like export controls, regional chip requirements. It adds a whole new layer of complexity.
Which leads us perfectly into our final knowledge gap. The last big question for you, the listener, to ponder after this deep dive.
Okay, what should we be thinking about next?
Knowledge gap 3, policy and competition. We know NVIDIA's current position relies, in part, on navigating complex global supply chains and export rules. So, looking beyond the current headlines, what specific new policies or industrial regulations are emerging globally? Think Europe's CHIPS Act, or similar initiatives in Japan, India, elsewhere. Which of these are most likely to significantly accelerate or restrict the development of regional, self-sufficient AI hardware ecosystems and supply chains?
And how would that potentially shift the competitive balance maybe 5 years down the line?
Exactly. Understanding those emerging policy dynamics is going to be absolutely critical for predicting who the major players will be in the next phase of AI hardware. Keep digging into how all these pieces, of course, the silicon, the software, the network, the power, and the politics interconnect. That's where the future of computing is being forged.
Fantastic stuff. A lot to think about there. Thanks for diving deep with us today.
Always a pleasure.
We'll see you next time on The Deep Dive.